We've talked about the traveling salesman problem a couple times, but again, the idea is that you want to visit all of the locations on the graph. So let's assume all the locations are cities, and so the traveling salesman problem, which I have abbreviated TSP here, the problem is that if all the cities are connected, if you can get from one city to any other city on the map, there are n-1 factorial possible paths, and that's just not feasible to check them all, because for any reasonable size of n, that just becomes too cumbersome. Now, of course, usually all cities aren't connected directly, but that gives you sort of an upper bound on how bad the problem can get. So the approach we'll use is what we call the nearest neighbor algorithm, and the nearest neighbor algorithm is very, very simple to run. The way it works is you start at any city you like, and then you visit the nearest unvisited city. So the nearest city you haven't visited yet, and then you just keep doing this until you're done. So let's show an example to see how this works. But before I do, I'll mention that this kind of algorithm has a name. This is what's called a greedy algorithm. And the idea behind a greedy algorithm is that it basically optimizes at each step. It picks the best choice that's available at each given step. So the reason it's called greedy is that it's not looking forward to figure out what's going to be most efficient in the long term. It just looks at this step, what's the most efficient thing to do, and then it takes that action. And then after doing that, it says, okay, now what's the most efficient step, and it takes that action, and so on. So that's exactly what's happening here. This nearest neighbor algorithm says, take the shortest path that you have available to you right now, and then once you've done that, reevaluate and take the shortest path you have next, and so on. So for example, using our map of these airline routes, let's say we're starting over here in LA, and we want to visit every city that's shown here with as short a path as we can find quickly. And so the nearest neighbor algorithm says, starting at LA, let's find the closest neighbor. So of the three options, the shortest path is up to San Francisco. So we go up to there. Then at this point, we look and say, what's the closest thing to San Francisco? Well, of course, LA is the closest thing, but we've already visited that. So we're looking for the closest one we have not yet visited. So of the three options left, the three paths we can go down that we haven't covered yet, we have the shortest path goes to Denver. So we'll go to Denver from there. And then from Denver, again, we look and say, what's the shortest path? Again, the shortest path here would be back to LA, but we've already visited that. So the shortest distance to an unvisited city is to go out to Chicago. And then once we land in Chicago, we look and say, what's the shortest path now to an unvisited city, which would take us down to Atlanta. And then from there, the shortest goes down to Miami. And then from Miami, there's only two options, one of which we've already covered. So we're going to take the other one up to New York. And then finally, Boston is the last city left to be visited. And so if you look, you might be able to find a more efficient route through this, but it's pretty good. We've gotten a decently efficient route. Certainly, there's no glaring inefficiencies to this, no sort of out-of-the-way trips that we wouldn't have expected. So again, you may be able to find better routes, but it works fairly well. So the nearest neighbor algorithm, while not, again, necessarily perfect, gives us good results with a pretty easy process, a pretty short amount of work that we actually need to do. Then we can do another example. Here we're going to find the shortest Hamiltonian circuit. So remember, the Hamiltonian idea is just this idea of visiting all of the nodes, so exactly the same as the traveling salesman problem. And we want to start at A and find the shortest circuit to come back to A. So again, using the nearest neighbor algorithm, starting at A, we would take the shortest path over to D, and then from D, there are two options left to go, one up to B, one over to C, and of the two, the shorter path is up to B. with a weight of 6 instead of 7. And then from B, we have just one node left unvisited, so we'll go over to C and then back up to A to complete the circuit. So if we didn't need a circuit, we would have stopped at C, but we're asked specifically for a circuit here, so we'll come back all the way to A. So the traveling salesman problem, again, there's no general solution that gives you a guaranteed optimal route, but the nearest neighbor algorithm works decently well. It's very easy to run, and it gives you pretty good results, as good as you can expect under the circumstances.